Good morning. Today is Friday, October 11th, 2013, and today's topic is Special Relativity, Part 2, The Paradoxes. So let's get started with an understanding of space-time, because we're all familiar with 3 dimensions of space and 1 dimension of time, but Einstein gave us a 4-dimensional space-time, which isn't like 4 spatial dimensions, it's a little more complex. If we take horizontal measures along the x-axis, it doesn't make sense to call them seconds, any more than it makes sense to call a vertical measurement along the time axis meters. So what's sometimes called proper time or proper distance should more accurately be called the proper space-time interval. So while the surface of time has a negative tilt as it moves through space, it can be measured invariably through any observer. Now let's use that to plot the different space-time events as seen from different observers in the ladder in the barn paradox. The question is, can you use the relativistic effects of spatial contraction to fit a ladder into a barn when it's actually a little longer than the barn itself? For our purposes, we'll use a spaceship instead of a ladder to demonstrate the same principle. The trick is that the barn and the spaceship are moving relative to each other, so they should each appear spatially contracted in each other's observations. Can they both be right? Well, the key is that they work in 2 different inertial frames, so they'll observe 2 different states of simultaneity. We see in this diagram that from the observational frame of the barn, the spaceship is spatially contracted and therefore it fits inside the barn according to the barn's definition of simultaneity. Let's say at a time surface of t equals 10, the barn was able to blink shut its entrance and exit doors simultaneously. This would confirm that the contracted ship was completely contained within the reference of the barn. And let's say the doors can blink themselves back open just as fast, so the ship doesn't hit the doors with the force of an atom smasher. But the ship's frame of reference tells a completely different story, since it would never fit inside a barn that's contracted to half its size. The ship is in a different frame of simultaneity, so the space-time coordinates for the entrance and exit are different surfaces of time. So if the barn's clock says that both doors closed at t equals 10, then the ship's clock could say that the nose reached the exit at t prime equals 8, at which point the exit door alone instantly shut and reopened. The ship continues out the barn, and only later does the tail clear the entrance at t prime equals 10. Now let's take a look at the twins paradox, where we'll meet our identical twins, Al and Bert. Bert's an old homebody, but Al is a rocketeer, and he's going to take a trip from Earth to a planet 10 light years away we call Proto-Mars. Now this is relativity, so you'd think that having the same speed relative to one another would leave an effect that's completely symmetrical in both time dilation and spatial contraction. But there are 2 important differences for our twins that will radically change the outcome. The first is that Bert remains in the same inertial frame as Earth and Proto-Mars, so he doesn't experience any of the spatial contraction between the worlds. The second is that while Bert remains in 1 inertial frame, Al travels in 2 frames of inertia. In 1 frame, Al is traveling from Earth to Proto-Mars through contracted space and decides to either stop for tea and crumpets or turn the ship around and head back to Earth. It doesn't matter which Al decides, because the moment he changes his velocity, he's going to alter his frame of inertia. In that instance of acceleration, his time surface of simultaneity can shift right past that of his twin, and 20 years can elapse in his frame's measurement of Earth. So Al has negated his red-shifted velocity, and he's now returning to Earth along a blue-shifted frame of inertia. Both twins can observe a sped-up compression of events in the blue-shifted light of the approach. But both can also measure time dilated against each other's frame of inertia. So when the twins get back together, more local time has elapsed in Bert's frame than has elapsed in the frames traveled by Al. Because the square of time is related negatively to the squares of space, someone